Now that we know the fundamental theorem of calculus part 1, let's practice using it. So how about we find the area under the curve y equals, let's say, e to the x above the x-axis between x equals 0 and x equals 2. Find the area underneath the curve y equals e to the x above the x-axis between x equals 0 and x equals 2. So we don't need a picture, but I'm going to sketch one anyway. We know what the shape of the curve is for e to the x. We're just going between x equals 0 and x equals 2. We want to find this area here. In terms of integral notation, we're going between x equals 0 and x equals 2. Our integrand is e to the x dx. And now that we have the fundamental theorem of calculus part 1, we don't have to go to all the trouble of breaking this up into little pieces and constructing rectangles and adding them all up. Instead, we just need an antiderivative for e to the x, a function whose derivative is e to the x. Well, that's easy. E to the x is a perfectly nice antiderivative of e to the x. The derivative of e to the x is e to the x. We'll put in the 0 and the 2. So this just means e squared minus e to the 0. In other words, e squared minus 1. And we're done. The area of this is e squared minus 1. If you want a decimal value for that, plug it into your calculator. Let's do another one. Let's find the area under y equals sine x above the x-axis between x equals 0 and x equals pi. We sort of considered this in an earlier lecture, so we know what y equals sine x looks like. We know sine x is just this oscillating curve. And we want the area of this bump right here. We talked about this briefly in an earlier lecture. We can see that it sits inside this rectangle whose height is 1 and whose width is pi. That area, that whole rectangle is pi. So the area of this bump's got to be less than pi. Let's see what it is. We're going to integrate between 0 and pi sine x dx. We're looking for a function whose antiderivative is sine x, while a function whose antiderivative is sine x is negative cosine of x. And we're going to plug in x equals pi and subtract off what we get when we plug in x equals 0. If you're wondering, wait, what's that minus sign doing there? Remember, the derivative of sine is positive cosine of x, but the antiderivative of sine is negative cosine of x. So anyway, this is going to be minus cosine of pi minus cosine of 0. So cosine of pi is negative 1, minus cosine of pi is 1. Cosine of 0 is 1, so this is minus 1, but minus 1 is plus 1. 1 plus 1, 2. The area of this bump works out to exactly 2, which of course is less than the area of this whole rectangle, which is pi. Let's do some more. Let's integrate between 1 and 3 x squared plus 2x plus 5. We don't have to work very hard for this. We're looking for an antiderivative. Antiderivative for x squared is 1/3 x cubed. The antiderivative of 2x, antiderivative of x would be x squared over 2 times 2, so that's just x squared. Antiderivative of 5, 5x. You could put in a plus constant, but it's just going to cancel out when you do your subtraction. So I'm just going to choose the easiest antiderivative I can. And we're going to plug in x equals 3 and subtract off what we get when we plug in x equals 1. So this is equal to 1/3 times 3 cubed plus 3 squared plus 5 times 3. I'm going to put that in parentheses, minus, I'm going to plug in the 1 now. I think I might have to get rid of some stuff over here, so I have room. Minus 1/3 times 1 cubed minus 1 squared plus 5 times 1. And after this point, it's certainly just arithmetic, but let's just go ahead and work this out. So 1/3 times 3 cubed is 9 plus 3 squared, that's another 9, plus 15 minus 1/3. Oops, I don't know why this is a minus sign. That should be a plus sign. My mistake. 1/3 plus 1 plus 5. And let's see. We have 9 plus 9 is 18 plus 15 is 33 minus 6 1/3. So what is that? 26 2/3. If I've made an arithmetic mistake, you'll have to forgive me. But using the fundamental theorem of calculus part 1 is easy, provided that you can find an antiderivative for your integrand.